Okay, so thank you. So I will talk about learning quantum models from classical or quantum data. So as you of course all know, there's a great success of machine learning, as already was mentioned. We have this fantastic success of AlphaGo, where we get superhuman level playing of games actually from zero. I understand that it's now also possible for chess, which is learned completely from tabula rasa. So this is very exciting results. Also, there is this new thing from DeepMind called Agent 57. That is a recent thing coming out this year, where in fact all the Atari games are now learned to a very high level of sophistication. And of course, there are many spin-off of this technology to all kind of machine learning areas and application areas, and AI areas, and so it's very important. So in my view, in fact, the machine learning research questions is all about probabilistic inference. So, for instance, I've put here some examples. Whether you have some sort of a Markov random field, which you use to encode some visual pattern recognition problem, you have to compute some local statistics given this whole stochastic network, or whether you have a directed graphical model, such as given here in the middle, that may be used for some medical diagnosis, where you have many variables and you want to compute the probability of certain diseases given symptoms of patients, or whether you have a deep neural network, here in this case a variational autoencoder, there where you want to compute these things. In all these cases, you have to compute statistics in these models, and these statistics tend to be intractable. And of course, and I think so. This is the main bottleneck. This computational issue is the main bottleneck to advance the machine learning research and the performance. And so this is where you either use very expensive computers or you try to advance in some other way. Now, the way that is currently done is use, of course, Monte Carlo sampling. So here you see a picture, a snapshot of a ferromagnet near the phase transition, and you have areas to the array. You have areas of spins up and areas of spin down, and this problem is characterized by having two phases, and this is all the spin up and this is all the spin down state. And basically, you need to sample in this very large space with very many local minima, and there is a problem of mixing times to get a representative sample of this problem. And of course, as we all know, this problem is very hard and takes a long time. So the problem is to get to how to make this estimation of statistics in such model makes it more efficient. And what comes to mind is the quantum picture, where you say, okay, let's represent the so in the quantum case, you can have a quantum wave function that has in a certain representation, in a certain basis, will have a state vector which has certain non-zero components, and all these non-zero components in this quantum system are present at the same time. So we have a sort of, whereas the Monte Carlo is a sequential, where you visit one state at a time. Here you have all the states that you're interested in, you have them present simultaneously. And so would it be possible to use this quantum wave function as a representation of the probability distribution, and then somehow use that for the computing the statistics? So once you succeed in representing a probability distribution in terms of a quantum wave function, then you could imagine that you perform this several times, and each time that you prepare this wave function, you can do a measurement on that, and then you get independent measurements on that, and that would give you then the statistics rather than doing the Monte Carlo sampling. So this would be a completely alternative way to do this. So the problem is then, of course, how to map this probability distribution onto this quantum wave function. And this is, in fact, the problem of the quantum Boltzmann machine. So how can we design a Hamiltonian such that its ground states represents a given probability distribution. And so this is a learning problem. And so one way to represent this is to say, okay, instead of talking about wave functions, we talk about the density matrix, and we write this density matrix as a in this exponential form, where H is a Hamiltonian, and this is a matrix exponent, and Z is a number, just a scalar. It's a normalization such that the trace of this operator of this density matrix is equal to 1. And this, we parameterize this Hamiltonian in terms of small contributions. So think of these HR as single spin terms or two spin terms. These are operators, and these WR are numbers. And so the problem becomes that now this density matrix is parameterized by these numbers, and we have to find the numbers in such a way that this density matrix represents our classical probability distribution as good as possible. So it's therefore needed, in order to compare this density matrix to a target, we have to represent our target. It's convenient to represent it also as a rank 1, as a density matrix. And so one way to do that is to represent it as a rank 1 density matrix. So let's say that we have a probability distribution Q given. Then we can build a wave function out of that in a certain representation to have these kind of amplitudes. We can also add a phase factor here, but I have ignored it here. You can add a random phase factor, state-dependent random phase factor here. And then you build a rank 1 density matrix out of this. And then the learning problem becomes to find the row that is closest to this eta. So this will be the learning problem. And one way to define that is to minimize what is known as the relative entropy between these two density matrices. So eta is the data density matrix, rho is our model density matrix, and we minimize this. So this function now becomes a function of these parameters WR, and we can do gradient descent on this quantity and do the learning in this way. So in this proposal, if you make this the data density matrix, it's interesting to look at what happens to the statistics that you can compute, the quantum statistics of this model. So suppose that I have some operator A, and I want to compute the statistics under this data density distribution. So then I get, if I just write it out in this representation, I get trivially, I get this expression here. And you see that if A is a diagonal operator, this becomes also diagonal, so you get basically Q of S. So then you get classical statistics. So if A is a diagonal operator, you get classical statistics. If A is a non-diagonal operator, you get something else that that are also computable from this classical distribution Q. So this proposal here is a strict generalization of classical statistics to include quantum statistics. So in doing it in this way you can get quantum statistics in this classical data Q of S, and they can be used as part of the learning problem. So in short, the classical statistics are linear in Q, and the quantum statistics, so these are normal expectation values, and the quantum statistics are quadratic in the square root of Q. Okay, so let's take a particular case. So suppose that we have a spin model where we have Pauli spin operators, and we have our H is composed of single node terms and two node terms, and we have parameters W, which are the WRs that we had before, and we allow the arbitrary couplings between all the spins, all the pairwise interactions. And so then we can compute the gradient of S, as I said before, and if you do that, it comes out this very, very simple expression here. So it is the gradient consists of a difference of two terms, which is the statistics of these terms in a Hamiltonian. So this the parameter Wi is this parameter, and its gradient is proportional to this to expectation value of this particular operator, computed under the data distribution and computed under the model distribution. So during the learning, of course, this one will change fixed because it's given, and this one will change during the learning. And learning will stop when this difference is 0. In other words, you will learn a density matrix such that its statistics that are specified by this particular Hamiltonian, such as these statistics are equal in the model and in the data. So this is if your data density matrix is given in terms of in this way, and if Q itself is an empirical distribution, which is given by an actually finite data set, then the computation of these data terms, they are linear, or maybe with some log correction term close to linear in the size of the data set. So these are easy to handle. Of course, the hard ones are these ones, which are the one under the model, which have to be computed using the density matrix, and it scales, of course, exponential with the size of with the number of variables. Okay, so here you see an example of applying this model to learning neural data. So these are 116 neurons from the salamander retina. And this retina is exposed to some natural video images of natural scenes that salamanders like. And so these are the neurons, and so you get this kind of particular thing. So this represents so we're now learning the stationary distribution of these neurons. So these are so our Q of S is basically the stationary distribution of this whole thing. Because of computation, we can of course not do the whole 160, but we can only do 10. So we take 10 with some highest activity, and we're learning that data set. So here you see the training performance. You see S as a function of learning iteration, so it goes to a low value. Though it doesn't go to 0 because there is of course model mismatch. The model that we're considering here does not have to be completely perfect, so this arrow doesn't go to 0. And here I plot the picture of the rank of the learned solution. So if this goes to 0, the solution is essentially rank 1. And so this shows that over learning, this row converges to a rank 1 solution, which is close to the data, which is also a rank 1 solution. So this rank 1 solution can then be also, we can peel out a classical probability distribution from that rank 1 solution, and we can compute a classical KL divergence between that learned solution and the data distribution, and that's shown here. So if you do this with a classical Boltzmann machine, you get this KL divergence, which is quite high. If you use it with a quantum Boltzmann machine, you get this KL divergence, which is quite low. But what I want to show in this picture in particular is that in addition to the training data, I have about 28 test sets, which are they look similar to these. This was repeated many times. And this is showing the performance of these independent test data. And what I find exciting is that you see that not only this quantum model learns better, which could be an issue of overfitting, but it also generalizes better. And it generalizes better and it learns better because the difference is that it has these quantum statistics. And these quantum statistics in these classical data, they really do something. And they really improve not only the learning, but also the generalization. So they really have predictive value. Okay, so that's this example. So you can also learn other problems. So in this case, we're learning parity problems. So this is a very nasty, well-known machine learning benchmark, which is sort of the hardest problem that you can learn. It is defined in the unsupervised case that for each state you have a probability which is larger than 0 for an even parity state if S has even parity, and it is 0 if the parity is odd. So it is this in the hypercube, you see that every state of even parity is surrounded by states of odd parity, and so it's a very, very jagged energy landscape. So if you learn this with a classical Boltzmann machine without hidden units, of course you cannot, because what this learning is doing, it's looking at only at the 1-point statistics and the 2-point statistics in the data. And in the parity problem, the 1-point statistics are 0, the 2-point statistics are 0, the 3-point statistics are 0. Actually, all the statistics are 0 except the highest statistic, which is coupling everything, the 10 variables in this case. And that is, of course, not part of the learning here. And so therefore, actually, you can already predict that the classical Boltzmann machine without hidden structure will not be able to learn this. So you see that over here that we get again, with the classical performance of the Boltzmann machine is blue. You see that essentially we plot here the scatter plot of the probability of the states in the data versus probability in the model. And you see that classically you don't learn anything. But with the quantum Boltzmann machine, you get actually everything perfectly on this diagonal line, showing that it's very well able to separate the high probability states from the low probability states, which is 10 to the minus 50 machine precision here. So this problem can be learned spectacularly by this quantum Boltzmann machine, and the reason is sort of interesting, because note that in the quantum Hamiltonian that we use here, there is a sigma x term, and that is a two spin flip operator. And so the two spin flips is interesting for the parity problem, because if you are in an even parity state and you flip two spins, you go to an even parity state. So it's something that is very useful to learn the disparity problem, and it's an operator that is that's not present, of course, in the classical Boltzmann machine. So this is one of the reasons why this works so well for this parity problem. Okay, so we can talk about entanglement in these classical data in the following way. So suppose that we take this classical probability distribution and we can separate S in two subsets of variables, and we can compute the mutual information between these two sets of variables, and that mutual information is I sub C of Q. So we can do that. Alternatively, we can say, okay, we have this Q, we can go to this rank 1 density matrix that we just proposed, and then we have a quantum state, and from that quantum state we can also compute the mutual information, and that is I of eta. Now this I of eta is known to be this I of eta is, in the sense, this is a rank 1 density matrix. It has two components. It has so-called classical information and it has quantum information. And it turns out that for this case, the classical information is half of this total mutual information. And the quantum information is the other half of the total mutual information. Furthermore, it turns out that its classical information, so half of this quantum mutual information, is always larger than what you compute classically. And that's illustrated here in this figure. So here I take three variables and I divide them in two subsets, one of two variables and one of one variables. And I take random probability distributions on these three variables, and I compute the classical mutual information. I do this and I compute the quantum mutual information. I plot them as a scatter plot against each other. You see that the half of the quantum mutual information is always larger than the classical mutual information in this plot. They become equal in the case that the relation between S2 and S3 is deterministic. Then we get on the diagonal. So that's a saturating case. So we can do this either in this case where there is a random phase factor here, which I did not talk about before, that you get this picture, or you can have this phase factor 0, you get this. But in both cases, you get this enhanced sign. So this is something I have not been able to prove, but I believe this is true. We have done extensive simulations, but it's still out to prove this statement. So the fact that this classical information is larger than the mutual information computed between the two variables is illustrated very easily. You can understand very easily, because of course you can make a basis change. So if you make we take the basis and we change it to a new basis t through some unitary transformation, which is factorized over the two subsystems of that we consider, then if this is a unitary transformation, it induces a new probability distribution on these variables t. And so we can do such a transformation, and then consider the classical mutual information on this new implied distribution. And in fact, we can maximize, we can find a U that maximizes this classical mutual information. And by doing this, maximizing this, you can actually saturate this bound, and this I of C of Q tilde can be saturating this one. So by changing the basis in an orthogonal way, we can recover half of the total mutual information. So we get here in this picture, by doing a basis change, we can get here to this C, right? So that's what we can get with orthogonal transformations, which still leaves out the other half, which is the other half of the quantum, these so-called quantum correlations. And these cannot be captured by orthogonal measurement, as I just showed. But they can potentially be captured by non-orthogonal measurements. Now, so this is so if you take non-orthogonal measurements, the whole notion of locality of the two subsystems disappears because, as is well known, because of the violation of the Bell inequality. And that violation of the Bell inequality can be easily shown, demonstrated here, for instance, in this very simple case. I take two spins and I make the classical distribution completely correlated. So if spin one is up, the other one is up. If spin one is down, the other one is down. And I make a density matrix out of this by, sorry, this should be phi, as before that I did. And then I measure spin one, I measure it in the Z and in some theta direction. And this gives measurements A and B. And I measure spin two in the Z and the phi direction. And these give measurements A and C. And A and C, these two measurements A, they're fully correlated because of this particular problem density matrix I consider. And now I can compute the correlations. That's the standard Bell argument, or the CH-SH argument, that you can set up that you will find an inequality between the statistics that you observe. If there exists a classical distribution that describes the measurement outcomes on these non-orthogonal measurements, if such a distribution exists, then this inequality should hold. And if you do the exercise for this particular very simple case, and you compute this left-hand side and you plot it as a function of these two angles, theta and phi, you will find this plot over here, which has a certain point where you get larger than zero. In other words, you're violating this inequality, which means that there is that the statistics that are described by the system is not describable in terms of classical probability. So you get a violation of the Bell inequality in these systems, and this is related somehow to this other half of the mutual information, which is non-local, which is in these data. Okay, so of course, doing this program in software is highly intractable. Typically, so as is well known in physics, if you have a Hamiltonian, you want to compute some statistics of that. That is known as the forward problem. It's highly intractable, and the learning problem that we're considering is to go from the statistics to the Hamiltonian, which is the inverse problem, which in our case we solve by a sequence of forward problems. So we start with some parameters, we get a Hamiltonian, from the Hamiltonian we get some statistics. The statistics are put into the learning rule, they propose a change in the weights, this is fed in here, and so this is iterated in this way. So we get the complexity of the forward problem. And so we basically need to solve this forward problem somehow efficiently. And the way that we're exploring this at the moment is since we're trying to learn something that's close to a rank 1 approximation, we're using a rank 1 approximation throughout the training. We're trying that. And then we approximate this rank 1 approximation using some sort of variational approach, such as the Corleo-Troyer kind of variational approach to get. So then you get for each parameters, you have a learning problem which you have to learn such a wave function, sort of a double loop, inner loop to learn that. And we're exploring that with some mixed success. The other alternative is doing something called quantum belief propagation and extensions of that. And we were supposed to have a talk on that by my colleague, Eduardo Dominguez from Cuba, but apparently Zoom is not allowed in Cuba, so unfortunately we have to miss that talk for some later moment. But that's, I think, is actually very exciting work to have some sort of cavity approximation to compute these statistics. And of course, there is quantum hardware, and we're now looking at that. Also, we're doing something. We were looking at the D-Wave. It looks very hard to get this working on the D-Wave hardware. An alternative is to use a quantum circuit, and that is something that we've been trying. It's an approach which is using the QAOA that was mentioned in the last talk. And without going into details, so what the idea is that you make of course, you need to get a certain wave function, which is then your rank 1 approximation of your density matrix at that certain point in the learning. And this problem is then solved by variational, sort of a variational quantum eigensolver problem. And so you want to find the theta such that the current Hamiltonian minimizes this quantity is minimized, and so we use this variational quantum eigensolver idea. And here you see
we're now at 27 minutes.
Here you see some initial results of the performance of this learning over learning epochs. So there is this variational eigensolver is in there. And so in principle, if this would work, this could in principle scale up to large systems, because these expectation values can be computed efficiently on a circuit. You see that during the learning we still have large problems. This is not a very nice curve, but that's how far we are at the moment. This is done basically on this salamander retina data on five neurons, I think. Okay, so I'm done. I think the motto is let the quantum physics work for you. This is what we would like to propose, of course, in this ALICE program. In the case of the quantum Boltzmann machine, we use the quantum wave function to implement a probability distribution. The quantum features can improve the machine learning, so you get better models, you get better predictions, and you can go beyond probabilities somehow with this entanglement. But how to make use of that in models, of course, that's still understood. And we are need for physical systems to compute these things. So we need hardware, and of course that's we're excited to work towards that. And if you want to find more, you can read more about in this paper. Thank you for your attention.
Thank you very much, Bert, for your fascinating talk. We have already some questions. With respect to time, we were very fast. Well done. So we will certainly use up at least 5 more minutes for discussion, maybe even 10 if people are patient enough to wait a little bit after midday. So the first question is from Jalil, asking, how do you extend the contrastive divergence learning procedure in classical Boltzmann machines to a quantum Boltzmann machine?
So the contrastive divergence is something that is actually sort of it's sort of a hack, right? It is what the contrastive divergence does is say, well, I don't have time to run my chain to convergence. I just stop it after a few iterations. And Hinton has tried to convince me of that is a good idea, and maybe it's a good idea for the restricted Boltzmann machine, where he proposes it for, and I think this may be true. I don't know, but I think my understanding is that its success is somehow tied to the restricted Boltzmann machine, the 2-layer bipartite graphical structure. So in general, so here we're talking about fully connected models, and I don't think the contrastive divergence is actually working. And in fact, the gist of this talk is that you want to get rid of such a Monte Carlo scheme altogether.
While others are no, okay, we don't have a new question for the moment. Then I will. We have a question from Ricardo asking, commenting first, a great talk. Can you comment on the computational bottlenecks of your approach?
Yeah. So there is. So the computational bottleneck is in fact is this forward problem, right? This is the computational bottleneck. So given a Hamiltonian, give me the statistics. And classically, we know this is for a spin model. It is just a Gibbs distribution, and it's the Boltzmann distribution, and we know it's intractable. Here in the quantum case, it is quadratically more. So classically, you get 2 to the n. Here you get 2 to the 2n. So it's significantly worse. This is the computational bottleneck. I'm not sure what Ricardo wants to ask more. Maybe you can talk or speak up.
Florian asks, can you say again why, for instance, the parity problem is solved so well by the quantum Boltzmann machine, even though it only knows the 1/2 spin particle statistics? Is there, so to speak, some inductive bias built into the construction?
So indeed, so this is the learning rule, and the parity problem can solve this problem so well. The quantum Boltzmann machine can solve this problem so well because it has access to the quantum statistics. And the quantum statistics are these, for instance, what I said, these 2 spin flip statistics, saying that if you're in an even state, you go to an even state. So they are informative. So the classical Boltzmann machine only has these learning rules for k is z, and the quantum Boltzmann machine has them for k is x, y, and z. Right. So the quantum Boltzmann machine has 3 times as many variables as the classical Boltzmann machine. And but it's not just this larger number of variables. It's in this particular parity problem. It is that the structure of the quantum Boltzmann machine with pairwise interaction is very suitable for learning this problem. I should point out one thing though. I glossed over that. That is, in this quantum Boltzmann machine. In fact, if you learn this and you give all the even parity states, if you give them all the same probability, and all the odd parity states, you give them probability 0. In that case, if you do the learning, you will not find a rank 1 solution. You will find a rank 2 solution. And the rank 2 solution is an equal mixture of the even parity solution and the odd parity solution. Because actually these quantum statistics, they single out the parity problem, but it cannot decide on the sign of the parity problem. So it will learn both the even and the odd one in its solution. So it's a rank 2 solution. So what I did in order to generate these results is that I added an external field which breaks that symmetry, and then it learns one of these components.
Very good. Next question is from Max. Just to be sure, when you test the system on test data, you compute classical log probability on the classical data points?
Classical, sorry?
When you test the system on the test data, you compute the classical log probability on the classical data points?
Yeah, so here this is KL divergence. So in the case of the classical Boltzmann machine, it's clear, it's a probability distribution, and you compute the KL divergence between the learned probability distribution and the empirical test distribution, right? So that's these things. In this case, in the case of the quantum Boltzmann machine, we make use of the fact that the solution is very close to rank 1. And so from the rank 1 solution, you can just by squaring that rank 1 solution, you get a probability distribution out. And that probability distribution is then used as a surrogate for this classical comparison here. So so that's how that is done.